This is AQMF revision seminar talking a little bit about binomial distribution. So possibly I should spend just a second or two looking up binomial distribution in the book and hope that it's actually there so I get the appropriate bits right. Because that's... Let's look up 5... Wait, almost exactly. So, if x is a variable that assumes a value between 0, 1, 2, up to n with probability associated with some horrible expression, then x is called a binomial binomial variable. The value of x and their corresponding probabilities described above form the binomial probability distribution. So, seriously? So one of the things, when I was doing a little bit of reading up last night, it actually asked for 4 assumptions of the binomial distribution. So, So for something to be a binomial random variable, so it must be discrete. Nobody puts it. So that is, must assume a integer value. So all right. So, so my binomial random variable, number between 1 and n, where n is fixed beforehand. All right. So, typically this corresponds to corresponds to so we'd say it corresponds to the number of successes from n trials. So like flipping a coin n times, how many times did it come up heads? So if I define that my definition of success is heads, then that's where this thing comes from. So, for example, Ricky Ponting, Australian cricket captain, would always call heads at the coin toss. One of those things, people go on, Ricky, you always call heads. And he's like, well, I read that it doesn't matter which one you call, so I always call heads. Takes the decision out of it. Don't have to go up there and stressing about what I'm going to call. I'm going to call heads. Seems like a great plan. So, as far as Ricky was concerned, number of successes, number of heads. So, when we're doing this, the trials must be independent. That is, that the one before had no bearing on the subsequent trials. So if I had success in the first one, it should not change whether I had success in the second or third or so on. All right. So trials are independent. So that means I have a constant probability of success. All right. So also means that I have a fixed number of trials, which is going to be n. Constant probability of success, which we're going to refer to as p. Now, so my trials are independent, probability of success is constant, the number of trials is fixed. You know, I was thinking there should be 4 things I should be saying about it. So, anyway, so if my x, we say is distributed like a binomial variable with n trials and probability of success p. So, okay, so we should be able to see that my binomial distribution nice and simple. What was I going to say? Yay, sweet. Okay, so don't like this book. So what I want to do, if I have my probability of my random variable is equal to some number r, because it's a binomial distribution, I should be able to go, I know that this is going to be n r, so this is r successes, so it's p to the power r, and the number of failures, so 1 minus p is the probability of failure, and this is n minus r. So this is actually getting me the probability of one definite value. So I'm just going, I wonder if we can do this. So in terms of what you have to do, what we're trying to do is we have to first identify if we have that situation. So do we have a repeated trial? Are the trials independent? So so a good example is, well, one of my favourite examples is, I think it was the 2005 Ashes Tour of England, where Ricky Ponting won 2 out of 13 tosses. All right. So on pitches where the winning the toss determined who won the game, he won 2 out of 13 tosses. So we're going to assume, so my n is equal to 13, my probability of success we're going to say is equal to 0.5. Okay? Winning the toss should be 0.5. Now, we're going to assume that these events are independent. The coin toss at a cricket match is supposed to be the most random event that we can have to start the game, so that any advantage there is randomly assigned. Yeah? So let's go with, so So we're covering the details. So we've got a fixed number of trials where events are independent and the probability of success is constant. So this qualifies as a binomial distribution. So this x, the number of coin toss wins should be binomial distributed 13 and 0.5. So, probability x equals 0. We've got a nice natty formula up here. We're going to have 13, 0, 0.5 to the power 0, and 0.5 to the power 13. So this number here is going to be 1. So 13 choose 0 is 1. 0.5 to the power 0 is 1. And 0.5 to the power 13, who knows? Should be equal to like 1 on 8,192. Alright, everybody happy with that, yeah? Nod wisely and say yes. Alright. Probability of x equals 1. So again, I can just follow the formula that we've got up here. My 13, 1, 0.5 to the power 1, 0.5 to the power 12. 13 choose 1 is actually just 13. We'll go through doing that in a second, and this is by 0.5 to the power 13. And so this is equal to 13 on 8,192. Hope I've got that right. Well, maybe 2024, 2048, 4,009. Yep, sweet. So, one last one. X is equal to 2. 13 choose 2, 0.5 to the power 2, 0.5 to the power 11. This is actually going to be 13 times 12 on 2 times 0.5 to the power 13, which is going to be 78 on 8,192. Sweet. So, probability of winning 2 or fewer tosses out of 13 should be 78 on 8,192 plus 13 on 8,192 plus 1 on 8,192, which should get me 92 on 8,192. Don't really know what that number is. About 1 in 90. Is that right? Alright, waiting for people to tap on their calculators. Twiddle our thumbs for a second. I reckon about 1 on 90, or about point, what is that, 0.101 sort of thing? 0.101, something or other. We should actually make sure people check this calculation before they believe me, but that's approximately what it is. So, so we'd say that that was unlikely. Not necessarily unbelievable, but unlikely. Alright? So, now, what we're going to do, you guys have done normal distributions, have you? So the next thing to do with the binomial distribution is to talk about, is to go to talk about the normal approximation to the binomial distribution. So we've got, and I'm up to page 10. Awesome. So, one of the things that it doesn't say here, oh there it is, awesome. So, x is distributed like binomial of n p, then we'd say the expected value of x is actually np. Or if you like, we'll call that mu, the mean. And my sigma is known as square root of n times p. Some people write n times p times q, which is the same as writing n times p 1 minus p. So my standard deviation is n times p times 1 minus p. Okay. So if I go back to my example, the expected value, 13 times 0.5, which is equal to 6.5. Fair enough. We're all happy with that. And my sigma should be equal to square root of 13 times 0.5 times 0.5, which is 13, square root of 13 on 4, or square root of 13 on 2, square root of all of 13 on 4, or the square root of 13 divided by 2. Now, this means that it's approximately normally distributed. So this is x is approximately normal with mean 6.5 and standard deviation root 13 divided by 2. Okay, so we've seen that notation before. Nod wisely and say yes. Awesome. So, if this is normally distributed, I could work out whether it's got the we could do the same probability calculation. So before we calculated the probability, we said it's about 10%, for want of a better 10%, 0.1%, 0.1%. I know what I'm talking about. Really, I do. So if I do my z, should be x minus mu on sigma. I said my x was 2, my sigma was my mu was 6.5, and my standard deviation root 13 on 2. So this is going to be minus 4.5 on root 13 on 2. Oh, hey, sweet, distract him. You distract him for a second. There is a, what I'm going to do. Okay. All right. So I'm going to get my z, which is going to be equal to, so minus 4.5 divided by, and then square root of 13 divided by 2. So that's going to give me my z value. Okay, my z value of minus 2.49. All right, so just going to digress to Excel so that we can work these things out more easily. Sweet, I could have done that. Could have gotten the chart. Maybe I'll do the chart in just a second. And so this should be norm dist. And so if I do minus 2 point, screw that, that thing. Poo. What did I forget to do? X mean. So mean. So because I've done the transformation into a normal distribution, I'm going to use mean is 0 and standard deviation is 1, and I want it to be cumulative, so I'm going to use 1. Probability. Okay, so my probability here, this value here, is what I'd expect to get. To put that in contrast, we had the other value that we worked out was, what did we say it was? 92 divided by 8,192, 0.1123. Okay, so we should understand that sometimes my normal, when we're doing this, if the number of trials is not large, my normal approximation will not be good. Okay, so we've worked out this z value. Z value is equal to minus 2.49, and the p, according to our Excel, I'm going to write this and I'm going to 0.00628. This is for the normal approximation. And the p-value I calculated for the other one worked out to be 0.01123 other numbers. So I'm just going to switch back to the document camera now that I've written those numbers down. Document camera, come on, go. Sweet. Okay, so if we've got a small number of trials, we need to use the binomial distribution. So if the number of trials is small, we use So, in actual fact, there's a rule of thumb that says if n by p and n by 1 minus p greater than 10, then I can use the normal approximation. All right. So if my p is 0.5, then I need at least 20 trials before it's going to be a reasonable approximation. Is that helping us where we want to be going? Nod wisely and say yes.
So how did you know which table to use?
Good question. All right. So when I did the calculation on Excel there, the first part of that calculation was creating that z value. So what that z value does is it puts it into a normal distribution. So let's just pull this down a little bit here. So this calculation here transforms the x from being from this normal distribution to being from this normal to being from the standard normal distribution. So so let's just see if it tells me 986. So we quite often do that bit with the z value and calculate the standard normal distribution. Nope, doesn't have it in here. 600 was the other one. You know that thing where you want... Corey, do you have that chart handy? What textbook doesn't have that? What textbook? Decent textbook doesn't have it. So, if I'm doing it from the chart, nobody likes that. Let's do this. So if we look at the picture at the top tells me the z. Now, one of the things I'm noticing about this particular table is it's giving me positive z values. So all the values down here are the z. All these values are my z scores, and so the value inside the chart here is the probability. So my picture is telling me that I'm doing a cumulative, but for a positive value. So my value that I was looking at was minus 2.49. So I'm going to exploit the symmetry of the situation. So let's just give ourselves a new page and go 11. So what I'm going to do is I'm going to do a real rough sketch. And so the thing I've got is minus 2.49. That's my z score. All right, and what I want is this tail out here. Okay, whoops, there we go. And so in terms of this picture here, because it's symmetric, this is sort of equivalent to finding out this bit here. All right. So I can flip it over, so I can change. So there's nothing wrong with me just flipping that picture over and going, actually, rather than minus 2.4, I'm going to find 2.49, and I want to find that area there. So, but that's going to be 1 minus, and then in terms of the picture, I'm finding out all of this with my 2.49. So if I do 1 minus, now with this thing, so 2.4, whoops, go down to 2.4 here, awesome, just going to make it. And then I go across to the 0.9 here, that's working for you. And so if we go across to this one here, that's this term here, so 0.9936, 0.9936, and so when I do 1 minus 0.9936, I'm going to get 0.0064. And given what I wrote down before, that's close enough. Okay? So, so that's how we'd go about using the chart. So in terms of the chart, just this is like the first two, like, you know, place and first decimal place. This line across here gives me the second decimal place. All right. So if I'm trying to use it as an inverse, what I can do. So say I want to find like I want to find the cutoff for the first 90%. What I do is I actually scan through these numbers until I find the number closest to 90%, which we might say is 0.8997. All right here. And so if I follow it across, it's going to be the associated Z value would be 1.28. All right. So if the first 90%. Notice with these things, so this is, I want this to be 90%, including this tail here, and so this bit's going to be 10%. And so my chart reckoned that would be 1.28. Just by, so that's how we sort of go both ways with this. We can go from a Z value to a P value, and from a P value to a Z value. But you'll notice that every time I've done this, tried to draw me a sketch to work out what it looks like, so I know where I'm going with it. Okay?
Okay, I guess what I was asking then is, how did you know to use this table opposed to the other one where we were just trying to find?
So I said that it was a normal distribution, didn't I?
Yeah.
And so that means I'm going to use my normal table. All right? So you really don't have, I don't think you guys talk about many distributions.
Only opposed to that table.
So that's actually still a normal table. You've just got, that's the other side of Corey's, and I looked at that and thought, ooh, don't do that. Actually, I'll grab that back and I'll show the people what young Brian is showing me. So the thing is, this thing still says normal distribution. All right, see at the top there, it still says normal distribution. All right, but what you'll notice here is, like, when my Z value is 0, all right, when we're right at the center, I'm getting a probability of 0. That's saying that that area is 0. So it's going out, and if I go all the way down to the bottom corner, the p-values, the maximum p-value for that region is 1/2. So like I said, the distribution is symmetric. But this chart is only giving me that upper half. All right? So in the same way as what we did before, if I looked up my 2.49, so 2.49, I'm getting 0.4936, whereas before it was 0.9936. If I add the 0.5 to that, that will be the same probability value. Okay? And so this is actually a really important lesson. All right? One of the favorite pastimes of people giving statistics exams where they give you these charts is to give you a different chart. Okay? All right, these ones had all positive values in it. They might give you the one with all the negative values in it. So we're supposed to exploit a couple of facts. Firstly, that the distribution is symmetric around 0. So my standard normal, so sometimes referred to as a standard unit normal, has mean of 0 and standard deviation of 1. That is, half the values are less than 0, half the values are greater than 0. My standard deviation, my spread value, is 1. So that means anything beyond about 3, so less than -3 or greater than 3, my probability is effectively 0. Like if I go down into the region where my 3's are here, so 3's start here, these numbers are all 0.49 something or other, all right? So the closer they are to 0.5, the closer the closer this tail bit is to 0. And so and you can see from, if I get, so all the values after 0.39 are actually 0.5. So within the accuracy given in this chart, so that's 4 decimal places, these numbers are 0.5. All right, so if you, and you have with a standard normal distribution, have you talked about standard normal distributions? Yeah. Okay. So the thing is, we have this rule of thumb which says that for a normal distribution, 68% of values are 1 standard deviation away from the mean. 95 are 2 standard deviations. In fact, it's 95.5 are 2 standard deviations away, and 3 standard deviations covers 99.7% of all the values. So what that means is, if I've only got a relatively small number of I'm not getting anything that is more than 3 standard deviations away. There's actually a thing called Bernoulli's Theorem or something or other, which says, which is sort of like how many n you must have before you can be this many standard deviation away. All right. So the reason there is more nutters in the US is because there are so many more people in the US. There is a greater deviation away from the normal. All right. So, because there is the 400 million people, that allows me to say there are people that are 6 or 7 standard deviations away from the mean. All right. Whereas in Australia, that order of magnitude smaller in the population. In terms of social commentary, we should point out that doesn't mean that the people in the US are more crazy. It just means that in actual fact, there is the extreme, because there's so many that are normal. There is such a large proportion. There's more that 1 or 2 stand out more. So it doesn't say they couldn't. Yeah. No, don't do that. No. So getting back to this though, you've got to be careful about how you're looking at the chart. All right. So again, with this chart, we're only getting positive z values. So if I had a negative z value, I have to work out what that means in terms of my chart. I have to exploit the symmetry of the distribution, and I have to make sure I'm getting the right area. So I have to look at the little picture to get what area. You'll notice here how it says probability of z between 0 and sort of the z value worked out. All right. So this is actually some charts don't give you a picture, they give you this statement, and you need to be able to interpret that statement, okay, to get the right area. So we good? Okay. Any other questions about normal distributions?
So I guess if we relate it to the question, it's saying that there is a 0.0064 chance that he bowls or tosses.
He wins so this is saying, in terms of the question, the probability that he won 2 or fewer tosses, assuming a normal distribution, would be 0.64%. All right, sort of getting up there in terms of like 1 in 200. The other probability worked out sort of slightly less than 1 in 100, and that's probably a much more accurate probability. But in this case, we're going 1 in 200. In actual fact, if you go gambling, you should go gambling with Ricky Ponting in the UK because he can't win. Although maybe on the balance of probabilities, he's due for a couple of years. Anyway, so look. If we've not got more questions, we might call it a day there, because we're already at 3:30 according to the play school clock. Well, actually 2:30 according to the play school clock, but that means 3:30 in real time. Do we have? So we'll finish up there. Any more questions? No. Good to go. Right. So Mass Drop-In Centre open for the next 2 days, 10 to 4. Come and talk to us. Good luck with your exams, and we are actually open well beyond. We're open until something like the 22nd of November, so the last Thursday of the exam period. So we're going to